All right, so let's look at lab number 7. And in the last couple of labs, we were looking at basically analog circuits. So in this particular lab, we'll look at digital circuits and the gates, elementary gates like NOT gate and NAND gate and all that. These are the basic building blocks of digital circuits. And most of the digital circuits are implemented using complementary MOS technology. So we'll look at that. So this lab is all about using simulation as a tool to design and understand CMOS gates. All right, so so there are a couple of parts of it. And so in the first part, what we'll do is we'll make a CMOS inverter. This is an NMOS transistor here. This is a PMOS here. And so we'll make a CMOS inverter. And what we'll do is we'll use a 180 nanometer or 0.18 micron CMOS technology. And we'll use what is called as a fairly accurate model of the transistor called BSIM3 MOS model here. So we'll provide you with all the parameters of this particular model here. And so the simulation that we will carry out is pretty realistic simulation because the model is fairly accurate. And the results that we'll get will reflect what you would obtain on actual measurement as well. So what we'll do is, so we'll create the CMOS inverter and we'll use the 180 nanometer MOS model here, BSIM3 model here, and we'll look at the voltage transfer characteristics. And from the voltage transfer characteristics, then we'll find the maximum gain, the inverter threshold voltage, and the noise margins, the standard things that we can calculate or obtain from voltage transfer characteristics. And we would also suggest that you explore the voltage transfer characteristics and all the other parameters which depend on it, like these noise margins. They depend on the ratio of the PMOS and the NMOS transistors, so we would like you to explore that here. And in the subsequent parts, we'll look at the propagation delay of the CMOS inverter and propagation delay measured using different means that are there here. And finally, we'll look at a 2-input NAND gate here. All right, so let's open the simulator and see the different parts that we have to do here. All right, so we start off with basically an NMOS transistor is shown here and a PMOS transistor is shown here, right? So let me double click and show you. So when you double click it, we've called this NMOS BSIM. BSIM is the name of the model, and we've just named it like that, NMOS BSIM 018, meaning 180 nanometer here. And these are all the parameters that are there here. All the parameters of the model that are here. So the parameters which remain constant are all written here. And then there are parameters which change, so which we can write over here, right? So when you go to value here, so for example, we can write that the width of the Mosfet is 0.27 microns. Length, we will keep it fixed as it's a 180 nanometer technology. So the minimum dimension that you can get is 180 nanometer. So we'll keep that fixed at L equal to 0.18 micron. And then we have entered area drain, AD equal to 0.15. We'll come to that, 0.154 picometer square. And perimeter of the drain, PD refers to the perimeter of the drain. So this area drain and perimeter drain is needed to calculate capacitances. So you have to specify what is the width of the MOSFET, what is the length of the MOSFET, what is the area drain, and what is the perimeter drain. And once you do that, along with the basic parameters that are there, then the model is ready for you to simulate the transistor here. So as an example, we have this NMOS transistor here. The body terminal is connected to ground. And this 180 nanometer technology, the usual supply voltage for 180 nanometer technology is 1.8 volt here, which means that normally you would apply anything from 0 to 1.8 volt here. All right, so supply voltage is 1.8 volt here. Anyway, so what you can do is, and similarly, we have a PMOS transistor here. So what you can do is you can start off by simulating the NMOS transistor and the PMOS transistor. Simulating in the sense that you can look at, for example, the drain current of this NMOS versus the gate to source voltage. Source is grounded, so gate to source voltage here. So you can vary the gate to source voltage and you can see how the drain current varies. Or you can look at the drain current versus the drain to source voltage here. So let's do that here. So analysis, you go to DC here. And so note that the first thing, let's disable this here. So the first thing that we'll do is look at ID of Mn is the name of the transistor here. And what we are going to vary is VGN, the gate voltage here, all right? And we'll vary from 1.8 to 0 in steps of 0.01. So we are going to look at the drain current of the NMOS transistor here. Mn, see, Mn is the name of the transistor here, all right? So, and all right, so let's go back here. And so we can simulate auto scale. Let's run the simulation. Right, so this is how it goes here. This is the drain current along y-axis versus gate to source voltage here. So somewhere here around 0.5 or so, you can see here is the threshold voltage here. That's where the device starts, the current starts to become significant. Note that below the threshold voltage, the current, it appears to be 0, but that's because we have a linear plot. The current is actually not 0, which we can see this. If we go to limits here, and let's use a log scale on the y-axis here. All right, so log scale here. Let's remove this here. All right, so let's run it here. Okay, so now this is the data that we get here. So as I said, somewhere around 0.5 or so is the threshold voltage of the transistor. And so below this, all this region is what we call as the subthreshold region here. So the current is increasing exponentially here because there's a log scale here. So the current increases exponentially here. And this is the part here which is above threshold voltage. And in between is a transition region from subthreshold to the strong inversion region here. And because we've applied a drain to source voltage, if you go back and look at the maximum 1.8 volt, so our transistor is basically working in saturation region here. And so it's primarily in saturation region up to, most of the gate to source bias here. So it's in saturation region, and we expect it to be square law, but the square law kind of a behavior holds only for large channel MOSFETs. And you can go and explore and see what the behavior is. So we can go back here and convert it to linear scale again. And note that it doesn't look square law. It doesn't look parabolic here, right? So it's not exactly, and neither is it completely linear. So the behavior is somewhere in between. Anyway, so that's the characteristics that you can explore, ID versus VG here. If you wish, you can explore the current versus the drain to source voltage here. So we can do that also. So we can go back DC limits here. Instead of gate voltage, we can put here VDSN here. Change that here. And again, we vary from 1.80 to 0.01. So it's going to simulate ID versus VD because the x-axis would be VDS. So ID versus VD. For a fixed gate to source voltage. So in our case, the gate to source voltage is fixed to 1.5. And of course, you can change it if you want. All right, so let's see here, limits, IDMN, VDS, and let's run it here. Okay, so that's how it looks. So this is our standard ID-VD curve here. If you want, you can change the gate to source voltage here. You can do step. So you can step the gate voltage here, VGN. So we can step VGN from, let's say, 0.5 to 1.5, right? So let's do that in steps of 0.5, 0.5, and step it, yes. Okay, let's run it once more. Right, so these are the standard curves that you get here. ID-VD curve, these are for different values. So 0.5 is close to the threshold voltage, we don't get as much current, and then the current starts to increase. Anyway, so you can explore how the transistor behaves with respect to its transfer characteristics, meaning ID versus VGS, and with respect to its output characteristics, meaning ID versus VDS here. And similarly, we have the PMOS transistor here. So you can explore the characteristics of the PMOS transistor also. All right, so that's the first part, becoming familiar with the NMOS and the PMOS transistors. In the next part, what we have done is we've created a CMOS inverter. Right, so this is the NMOS here. And okay, so let's exit the analysis here. Okay, so this is the CMOS inverter here, NMOS here, and the PMOS here. And note that what we have done is if we go and double click NMOS size W, we have kept as 0.27 micron. And the PMOS size, we have kept it as double of that here, because PMOS mobility is approximately half of that of electron mobility. So we have kept the size double so that the current driving capability of both of them are close to each other, right? So we have this CMOS inverter, and now we can simulate it. We can, for example, vary V in and look at how V0 varies here. Note that the supply voltage is 1.8 volt here. All right, so we can do that. We can vary V in. So we'll vary V in here. Right, we'll vary V in from 1.8 to 0 here, and let's disable this here and look at V0 here. Okay, output voltage here. So let's run it. Right, so this is the standard voltage transfer characteristics of an inverter here. This is V0 here, and this is V in here. So you can determine, for example, the inverter threshold voltage. So inverter threshold voltage is if you draw a line V0 equal to V in here, a linear line here, and the place where it intersects, that's called the inverter threshold voltage. So we can find this out by a cursor here. So we are looking for where V0 and V in become equal, right? V0 and V in become equal. All right, somewhere. All right, somewhere here. So it's about close to 840 millivolt here. So note that we have 1.8 is the supply voltage. Ideal or symmetrical VTC would have given us half of 1.8, which is 0.9. In our case, we are getting 0.845, which is close to the value that we have here, right? So this is the VTC, and what you can do is you can explore the VTC here. For example, you could make the size of the PMOS same as the size of the NMOS, or you could make the size of the PMOS 4 times the size of the NMOS, and you can see what effect, what is the impact of all those changes on the voltage transfer characteristics. And if you would like to find out more about the VTC here, then what you can do is we can go back and limits here. You can differentiate it. So in this case, what we are going to do is plot the derivative. DD is derivative of output voltage here. All right. So let's plot that. So we'll keep it here, derivative, and let's plot here. Right. So this is the derivative of that particular plot. And from here, we can find out the maximum gain. Right, the maximum gain you can see here. So maximum noise margins and are related to this maximum gain here. So we get a gain as large as 28.6 here. So the higher the gain, what it means is the sharper the transition, and in general, the higher the noise margins that are there here. So the way to find noise margins are you find a place where the gain is equal to -1 here. So we can go here, Y, and actually write -1, and let's see here. Right, so okay, so first of all, let's go back here and Y and left. All right, so this is the place where you get gain equal to -1. So the voltage corresponding to it, this is what we call as VIL here, and similarly the voltage. Okay, so let's go back here, and again let's do the following here. So this is the other place where the gain goes to -1 at 930 here. So this is what we call as VIH. So from these threshold values, VIL and VIH, we can find out what is the noise margin low and the noise margin high. The noise margin low is simply VIL, and the noise margin high will be equal to VDD minus VIH here. So you can find those things by taking a differential of the curve here. So let's go back to this main VTC here, right? So we find out where the gain is equal to -1 here, and there would be a gain equal to -1 here. So from these two places, we find out VIL and VIH, and find out what the noise margins are. And you can study as usual, as before, you can study noise margins as a function of the ratio of these two transistors here, and you can see how the noise margins change with this particular ratio here. All right, so that's the voltage transfer characteristics. The next thing that we want to look at is the delay of the inverter here. So it's the same inverter driven by 1.8 volt supply voltage here. And here is where we apply a pulse input here, right? So we apply a voltage from 0 to VDD here, 0 to 1.8. And the rise time, so we give an abrupt input, almost an abrupt input. Rise time is 2 picosecond, fall time is 2 picosecond here also. Pulse width is 150 picosecond, and period is 300 picosecond here. All right, so we have chosen that so that we can see because the delays are of the order of, you'll see 30-40 picoseconds. So that's where we've kept it here. And we've also connected a load capacitor here. And the load capacitor is something, its value you can vary. So right now, let me put load capacitor equal to 0 femtofarad here. Note that normally, as we will see later on, the load of one inverter is maybe another inverter or another gate. And the load capacitance comes about because of the input capacitance of those particular gates that are there here. So all right, so let's look at the first, let's exit here. So we are going to do a transient analysis. We are going to do transient analysis, and basically we will look at the output voltage V out here, all right? V out and V in 3. But before that, this is where it becomes important, because in transient analysis, the delay primarily comes about because the capacitors charge and discharge. So it's important to model the capacitances of the transistor that is there here. And if you go back and look at the capacitances of a MOSFET, so if you take a typical MOSFET here, there are these capacitors gate to source and gate to drain, right? This is from the input side here, gate to drain and gate to source. And then there is drain to body, and then there is body to source here. Now body to source doesn't matter for us because the body is grounded. So the body here of the NMOS is grounded here, right? So this body and source terminal gets shorted here. So this capacitor doesn't matter here. The drain to body capacitor matters, the gate to drain capacitance matter, and the gate to source capacitance matters here. Now this is the schematic of a MOSFET. This is the layout of a simplified layout of a MOSFET here. These are the N plus region here. The green one is N plus source and N plus drain. And this is where we have polysilicon and the gate here at this particular place here. So when we talk about the drain to body capacitance here, we are talking about capacitance coming about because of this region here, drain here. Note that underneath the drain, there would be that p-type because drain is N plus, and underneath the drain, there is this body which is p-type. So there is a p-n junction kind of a capacitance here. And to calculate the capacitance, we need to know what is the area of this particular part here, area of the drain. And not only the area part, but there are electric field lines at the sides also. And so what we need to do is we need to calculate the sidewall capacitance here, right? So because of the fringe capacitances that comes about from the sides here. So we need to calculate the sidewall capacitance. So that requires the perimeter part here, right? So you need the perimeter and you need the area to calculate the drain to body capacitance. The gate to source capacitance is calculated from the length and the width information that we've already entered here. Similarly, the gate to drain capacitance here. But to calculate the drain to body, you have to specify the area of the drain and the perimeter of the drain here. So for an inverter, then what you need to do to calculate properly these capacitances here, one normally needs to do a layout here. So for example, we'll not go into the details. We've done a simplified layout of the transistor of this inverter here. This is our NMOS transistor here. This is a PMOS transistor here. This is the gate here. And this is where we apply input. This is where we apply output here. And so the whole layout has been done on what we call as a lambda grid, where lambda is half of the technology parameter when we call 180 nanometer. So we say 2 lambda equal to 180 nanometer. So lambda becomes 90 nanometer here. All right. So if it were a 1 micron technology, lambda would have been 0.5 micron here. So it's a lambda grid. And from this, then, this is where the drain is here, starting from here, this part here. So after doing the layout, one can calculate what is the area of the drain and what is the perimeter of the drain, the perimeter part here and all that here. Okay, so we'll not go into the details. We have given you the values that for the NMOS, use the area of the drain, which is 0.154 picometer square, and perimeter of the drain is 1.35. Similarly, the PMOS is over here. The drain area of the PMOS is somewhere here. And the area of the drain is for the PMOS 0.24 P and 1.44. And perimeter of the drain is 1.44. Sorry, this is 1.35 micron. Okay, 1.35 micron. And this is also 1.44 micron here. Okay, so correct that is in microns here. And the area of the drain and the area of the drain is in picometer square, while this is in microns here. All right, so to calculate the delay, you have to enter those values here. So note that we've entered it here. Area of the drain is 0.154 and perimeter of the drain is 1.35 micrometers here. Right, and similarly, we've entered the area of the drain of the PMOS and the perimeter of the drain of the PMOS here. If you don't enter area and the perimeter, then the capacitance, the drain to body capacitance will not be calculated properly, and the delay values that you will get will be, you will underestimate the delay here. Anyway, so let's run the simulation here. So let's do transient simulation, and so let's run it for 300 picosecond here, and we are going to look at here V out and V in 3. Okay. All right, we'll look at this one a little later. Sorry, we'll look at later on here. Okay. Something else is enabled. Let's get rid of that here for a moment. Now. Okay. So in black is our input here, pulse input here. And so when input goes from 0 to high, the output of course goes from high to low here. And then when the input goes from high to low, the output goes from low to high here. So from this falling part, you can calculate what we call as the high to low propagation delay here. When the output is falling from high to low, we call it tau PHL, high to low propagation delay. And from here, we'll call low to high propagation delay here. So the way to measure propagation delay would be to take a cursor here and go to the 50% point here. So basically we are trying to go to 0.9 here. So one way of going this is simply writing 0.9 here. Right, so it goes here 0.9 here. So the delay, because on the left hand side the input 0.5%, where it goes to 0.9 is almost abrupt. So it's at t equal to 0. So this is approximately the delay here, 14.65 picosecond here. Note that the time scale is in picosecond. So the delay, high to low delay is 14.65 picosecond. And similarly, you can measure the from 50% point VDD by 2 here to VDD by 2 here. And you can measure how much is the propagation delay, which is low to high here. And so this is high to low and this is low to high. And this propagation delay obviously depends on the load here. So for example, we have put 0 femtofarad. So suppose I put a load capacitance of 1 femtofarad here. Right, so we can see, all right, so earlier it was some 14 delay here. Let's see where it is. It's become 20.51. So the delay has increased, right? So you can measure thereby the delay of this CMOS inverter as a function of the load capacitor. And if you were to plot this particular delay, you would get something like this here. This is tau PHL, high to low delay. And this would increase with load capacitor in a linear manner like this here. Right? So the tau PHL for zero load capacitance is what we call as the intrinsic delay here. It is, you know, even if you don't connect any load capacitor here, the CMOS inverter still has a delay because of the internal capacitances of these transistors that are here. So that's the intrinsic delay here. And beyond that, we have the extrinsic part here, which depends on the load, and the delay increases linearly with the load capacitor here. So you can write the delay of an inverter in terms of, you can write a linear equation, which will have a constant part, the intercept part here, which is which you see here, plus a slope multiplied by the CL here. Right, so a linear equation can be written for tau PHL. Similarly, for TP, this is high to low. You can similarly get low to high propagation delay also. So high to low delay is caused by the NMOS, because NMOS causes the capacitor to discharge, while low to high, which means when the output is going from low to high, so it's the PMOS which is charging the capacitors here. Right, so you can study the propagation delay, tau PHL and tau PLH as a function of the load capacitor that is there here, and you can plot it out, and you should see a graph like this. Okay. Now, this is one way of characterizing the delay. The other way of characterizing the delay is where we have taken one CMOS inverter, connected it to another CMOS inverter identical to it, and another CMOS inverter like this here. So the delay is most realistic for the middle inverter here. Now note that delay is not that realistic for this particular inverter because it doesn't have a load. Typically when you have gates, one gate would be connected to the next gate here, right? So the delay, you know, the delay here that you would measure would be only intrinsic delay. Well, the delay that you would measure here would be intrinsic delay plus a load here, a load which is another inverter here. And compared to these two, here we are applying an abrupt input, and normally the inputs that would be applied to the gate will not be abrupt inputs. They would be coming from some other gates here, right? So in that sense, the most realistic delay value is of this middle inverter here, because the input is gradually varying here, and it also has a load here. So what you can do is you can simulate these three inverters in series here, connected like this, and you can measure the delays of this particular inverter, delay of this and delay of this, and you can see the waveforms and all of that is here and study here. So for example, but before that, note that if you go back here to this, so we said you can study delay as a function of CL, and besides delay, another important quantity is the power dissipation. And in a CMOS case, the primary power dissipation is what we call as the dynamic power dissipation. That comes about because of the charging. So whenever the capacitor has to be charged, the current has to flow through the PMOS, let's say, and it has a resistance, so power is dissipated here. Similarly, when the capacitor is discharged, so current flows through this NMOS here, and it flows through a resistor, so power is dissipated here. So you can also study the power dissipation part here. So you can study, for example, average, for one cycle, you can take an average and you can look at what is the power generated in the supply voltage here. Note that the supply voltage is VDDS here. So we can plot here transient limits here along with it, okay? And we can call it 2, so you can see it separately. All right, so that if we go here, now if we just go to the, so what it has done, it has averaged it over one cycle here. So we have applied one cycle of the input here, and on the right cursor it shows us the power dissipation, which is 37 microwatts. Average power dissipation in this particular circuit, 37 microwatts is the power dissipation here. Now what you can do is you can go back and you can change the load capacitor here. So for example, if I put 2 femtofarad, let's see what happens here. So power dissipation should increase here, because it mainly comes about because of, all right, so note that it has become 47 milliwatts here, 47 microwatts here. So what you can do is, besides the delay, you can also study how the power dissipation changes with the load capacitor, how the power dissipation, you can also vary, for example, VDD here, or you could vary the frequency here, and you can explore how dynamic power dissipation changes with VDD, with the load capacitor, and with the frequency of the applied signal that is here. Okay, so that's the other part that you can explore here. So coming back to the delay part here, we said that delay of the middle inverter is more realistic. So you can simulate V01, V02, and V03. All of these things you can look at here. So V0, so let's enable that. Let's disable these ones now. And let's enable V01 and V02 and V inverter here. Let's see. Right, so this is the input here, the abrupt in blue. This is the input here. This is the output of the first inverter, V01. So note that it goes in per this one here. This is the output of V02 is this one here. Output of the second inverter here. So to measure the delay, what you will do is you'll go to VDD by 2 point on this graph and VDD by 2 point on this graph, and you can measure the difference here. So you'll get the delay of the second inverter, which is tau p, high to low here. And similarly, you'll go to VDD by 2 here and VDD by 2 here, and you'll get to low to high propagation delay here. So you can measure the propagation delay of the second inverter, the first inverter, and the third inverter also, and you can compare. And you can see why, for example, the second inverter would have the largest delay as compared to this one and this one also, and should try to explain why these differences come about. One of the common ways of measuring propagation delay is to make a ring oscillator. So we've taken 5 inverters, 1, 2, 3, 4, 5. 5 inverters, and the output of the last inverter, we've connected it back to the first inverter here because they've been given the same label here. Right, so when you do that, you've made an oscillator here. And if you simulate it, you will see the oscillation occurring. So let's do that. Transient limits, let's disable this anymore. So we'll look at V08 output here, and we'll simulate it for a longer period here. Right, so this is the output here, output of V08 here. And we can show that the time period of this waveform here, time period, so you can measure from peak to peak here, the time period here. The time period is related to 2, n is the number of stages in the ring oscillator, for us is 5, and the average propagation delay. So an easy way to measure a propagation delay is to simply make a long chain of inverters. You can, this is 5, and but even 5 gives us a a fairly high frequency here. 5 gives us a fairly high frequency, and so high frequency sometimes becomes difficult to measure. So one could even make people sometimes make a 32. They can connect 32 inverters in a chain and then connect the output of the last one back to the input of the first one, and so that makes the frequency very easily measurable in the lab here. And then all we can do is after measuring the frequency of the time period, divide it by 2n, and we get the average propagation delay of the inverter that is there here. Right, so make this so you'll have to make a odd number here. So not exactly 32, but you'll have to make 5 or 7 or 9 or 11 like that. So try making a long chain of inverters and see how it behaves and measure the propagation delay by that means. And you can compare that propagation delay to the delay of an inverter, the middle inverter that you measure here, and see whether it compares favorably or not. Okay, so that's the part about the inverter. So with this, what you would be, after doing a characterization of this particular part here, measurement of delay and power dissipation, and before that the measurement of noise margins and inverter threshold voltage, and then making a ring oscillator and measuring the average propagation delay. So these are the means by which one characterizes a CMOS inverter. So after doing this, you would obtain a complete information on the CMOS inverter, how it behaves, what its delay depends on, or what the noise margins depend on. So you should be able to understand and answer all of those questions after you use the simulator to do these simulations here. And then you can use a similar approach to construct other gates as well. So for example, we have made a NAND gate here, a 2-input NAND gate here. So these are the Nmos transistors in series, and these are the 2 PMOS transistors, A and B, connected in parallel here. And this is the input B here, which goes to this transistor here, and this is the input A here, which goes here. And again, to simulate this particular NAND gate, especially the delay values, you will have to put in proper values of area drain and perimeter drain. So all the size information is given here. So because the 2 NMOSs are in series, so what we have done is we've doubled their sizes. Earlier, the size of each NMOS in an inverter was 0.27, so we've doubled it to 0.54 here. And so both the NMOSs are 0.54 micron. The area drain, perimeter drains are given here. And similarly, the size information of the PMOSs are all given here. So, if you double click, this is where you enter the size information value here. So you enter the width, the area drain, and the perimeter drain, all of those things you enter here. Okay. So once you enter all these values here, and then your CMOS NAND gate is ready and you can simulate it. And so again, what I would suggest is that you simulate the voltage transfer characteristics, the static characteristics first, and this you can do it in different ways. So for example, you could keep, for example, the NMOS A or input A to be high here, which is 1.8. And then you could vary the value of this particular input here. You can go from 0 to 1.8 here, and then see how the output varies here. And then from there, you'll get a particular VTC, and you can measure what the noise margins are. Then you can keep this at 1.8 here, input and you could vary VA here. So you'll get another VTC here. Or what you could do is you could simultaneously vary VB and VA here. Both the inputs are changing here. So you get actually 3 VTCs, voltage transfer characteristics, depending on how the inputs are being applied here. Whether one input is being varied and the other is kept constant, or both of them are changing simultaneously here. Similarly, you'll get different delays also here. So for example, VA could be 1.8, and this input you could switch from 0 to 1.8 here. And then you will get one particular delay here, right? So which means the delay that you're getting is from this input to the output here, right? So input to output delay here, you're getting here. Or what you could do is you could keep this at 1.8 or high, and you could switch this here, and you would get a delay from this node to this node here. And you'll see that the delays are in general different. The delay from input B and the delay from input A are different here. Okay, so you'll see that, and try to think of, you have the whole schematic before you, and you have all the results from simulation. Try to think of why this is happening, why the delays are different from the 2 inputs that are there here. All right, so this is the NAND gate here. Similarly, we can make a NOR gate and all the other complex gates as well. and we can study using this particular approach here. All right, so with this, so what along with it, what we'll do is we'll share the model of the transistors that are there here. So note that an easy way to enter the model parameters are, if you go here in microcap, you have all these models here. So you can enter the model right here. So we'll share a text file, and you can just copy the model parameters from there into this particular place here. So this is the model of the NMOS here, and this is the model of the PMOS here, and this is the name of the model here, right? So this is the name here, and these are all the parameters that are here. Okay, so let's stop here.